Right. Well, tonight we get to do lines and planes. Maybe a little bit more, we'll see. I'll say first, in the plane, in the XY plane, the parametric equations for a line come from the following prescription. You can consider a vector from the origin out to any point, x0, y0. Let's call that vector r0. And since it's a vector from the origin, it also has components x0, y0. But now, suppose we want a line that goes through that point. How can we get all the points of the line? Well, we could try it this way. We can consider all vectors points on the line by taking the vector. Actually, let's call this R0 going to x0, y0. And if we add to that a vector that's in this direction, let's say it's this vector B, some components A and B, that's parallel to the line, then we can get to any point on the line by taking an appropriate multiple of B, say this vector right here, T times V, maybe T is 2, it's twice as long, right, in this picture. So on the picture, maybe T is 2. But the idea is if I want to get to this point, I put T equals 3, or maybe this point, I take T equals 4.5. I could get out this way by taking T negative, adding minus a multiple of B to R0. But the idea is that this vector here now, R, a function of T, because for each T we can do this, equal to R0, the vector to this point on the line that we're given, plus T times the vector V, which is parallel to the line, now sweeps out all the points on the line by letting T run from minus infinity to infinity. All right? See how that works? If I put T equals 0, I just get R0, I get to this point. If I put T equals 1, I get R0 plus 1 times T puts me at this point on the line. So R would then go to this point. Here's maybe R equals R0 plus this. And so you notice that the terminal point of R of T, as T varies between minus infinity and infinity, sweeps out all these points on the line, right? For various values of T. If T equals 2, it goes there. Maybe this is T equals 3. This is T equals minus 1. This is T equals minus 2. And you sweep out all the points on the line by moving along R0 to here, and then some multiple of T sends you back, any multiple of T sends you back and forth like that along the line. So there's a prescription for a line as the terminal point of this vector R of T, which is R0, a vector to any point on the line, plus T, that we call a parameter, times V, any vector parallel to the line. All right, so we notice then that the vector parametric equations for the line, call it L, R, and so vector parametric form is R of T, this vector valued function of T, right? You put in T and you get out a vector of this, equals R0 plus TV, sweeps out the terminal point of R of T, As t runs from I sub infinity to infinity, sweeps out this line. Alternatively, since this is, when written down in terms of components, R of t has two components, right? X of t, y of t are the x and y coordinates of this vector R. So we'll just write out its components. Equals R0, which we said is x0, y0, plus t times the vector b, which we gave it components a, b. That's what that says. And so this says equivalently, by equating components, that x of t, first component on this side, is equal to the first component on this side, equals x0 plus pt. Similarly, y of t is y0 plus bt. So this is equivalent. Saying that the two components are equal is equivalent to saying that the two vectors are equal. We'll call this equation 2. And these are called parametric equations for the law. So you have a vector parametric form and a parametric form. We tacitly assume in here that t runs from minus infinity to there it is. Vector parametric equations and parametric equations for an arbitrary line L of plane. Who cares? It's not a big deal. We already know all about lines from algebra, right? Y equals mx plus t, I have slope m and y intercept t. Y minus y0 equals m times x minus x0 if it's you're given a point and a slope. And then there's a 2-point form and a general form. Why can't we just use those? And the answer is we can. However, now suppose we try moving this to 3 dimensions. A much harder game, right? In 3 dimensions, you don't say what's the slope and what's the y-intercept. It may not intersect the y-axis at all, right? Slope doesn't make sense because it can be, right? It's not just in a plane. It's in 3 space. And so, similarly, in 3 space, we do the same thing. Exactly the same thing. We consider any point whatsoever, which we can now plot x0, y0, z0 by dropping perpendiculars. The far end of the box is always where the point is, and so we can have an R0 vector going out there. And then the line runs through that. And if it has a vector direction v equals ABC, free space, we do exactly the same thing. If we take a multiple of v, maybe going out, here's TV, some number t. If you let t be arbitrary and add it to this one, you can sweep out all the points on this line. In other words, this vector here, r of t, back, I guess, is then R0, visible, R0, put end to end with TV, so it's plus TV, sweeps out the points on this line by letting TV arbitrary, right? This one with this one put end to end can go out however far down the line we want. And so it's exactly the same equations. R of t equals R0 plus TV. The same equation is there, except now V has 3 components and R0 has 3 components. Instead of 2. And maybe I should put it in just to be R0 goes to the point x0, y0, z0 on the line. B is now a vector in 3 space, so it has 3 components, A, B, C. So it's the same equation 1, just with these 2 vectors. And equations 2 becomes, by equating components again, right, it looks like this equation, except x0, y0, z0, abc. So there's 3 components to equate. And then what you get is x equals x0 plus at, y equals y0 plus bt, just like in there. But one more component, z is z0 plus ct. So in 3 dimensions, you just have one more component in the vectors and one more equation in the parametric form. But now you've got a great thing here, because now lines were hard to do in 3 space. This makes them very easy. So we can call this 2b. This is parametric equations for a line in 3 space. We just need those equations, and now we can do some interesting tricks. The lines are very easy. This won't take the whole period.
In the parametric equation, what's that variable at the very end? What's that called?
Oh, that's L. That's
Oh.
yeah, L for line. So it's a right line with a regular L. L looks like a 1, and so I just did that so it doesn't look like a 1. Thank you for clearing that up. Yeah. All right, so here's an example. Find parametric equations for the line in 3 space. 2 space works just as well, but when you see it in 3 space, you can see its utility better. Suppose I want an equation for the line going through the point 1, minus 2, 4, parallel. This is symbol for parallel in mathematics. To the vector with components 5, 3, minus 1. Well, I want a line through that point parallel to that vector. How do I do it? It's as easy as can be. If you were trying to think, how can I write an equation in x, y, and z? Generally, you can't. Right? And I just want to point out the problem. In the plane, when you write equations for a line, you write something like this: y equals mx plus b. Right? Here's slope intercept. For the general form, every line can be written in this form: ax plus by plus c equals 0, and with a and b not both 0. So every line can be written in that form. Every equation in this form with a and b not both 0 is a line. So you think, oh, maybe in 3 dimensions, this is the equation for a line, right? Guess what? We're going to find out either tonight or next time, probably tonight, that this is not an equation for a line. It's an equation for a plane. What happens in practice is each one of these equations reduces your dimension by 1. And so this is a 2-dimensional linear subspace and 3-dimensional space, a plane. Just like when you write a line equation like this, it reduces 1 dimension. You get a line in the plane, reduces your dimensions from 2 to 1. This one reduces your dimensions from 3 to 2. So we can't just write an easy equation for a line in 3 space like we could in 2 space. We could write 2 equations for plane and say, oh, it's their intersection. But then, boy, it's sure hard to see what the line is. It's hard to figure that intersection. So what we do instead is write parametric equations. And now you see why these are so good. In 2 dimensions, you don't need them really. We introduced them for practical purposes. You might use them once in a while. But really, these are for use for a 3 space. That's where you need them. So find a line through this point parallel to that. And it's easy as can be. You just say this is the point, x0, y0, z0. This is a, b, c, and it's just plug them into 1 or 2. If I say parametric equations, by equations 2, then x equals x0 plus at is 1 equals y0 plus bt is minus 2 plus 3t. And then z0 plus ct is 4 minus t. So easy it is to write out equations for a line if you just know the direction vector of a point. Those are parametric equations, and by letting t be an arbitrary number, I'll get all the points on the line. So these are very nice for working with a 3-dimensional space, and they work in 2 dimensions. How about this one? find this time vector parametric form 1. This is parametric equations here. Find the vector parametric form and parametric equations. Not for the line, but for, well, actually, let's do both. Let's say 1A, the line through 2 points, right? 2 distinct points determine a line according to Euclid's postulate. 2, 5, and 8, 7. I find that vector parametric equations for the line determined by 2 points. It's actually very easy. X0, Y0. I'll do this in the plane. X0, Y0. And what I think is I need a point on the line, and I need a vector direction following the picture. That's why the picture is beautiful. I just think you need a point, and you need this vector, and then you write down the equations, right? Well, the direction is very easy. You just write the vector from here to here is just v equals, subtract coordinates. 8 minus 2, 7 minus 5 gives us the vector 6, 2. This is your A and B. So now if in 2 dimensions, you write vector parametric form, you simply say by 1, the vector parametric form is R of t. This is the vector whose endpoint sweeps out the line. Is R0 the vector to this point? And actually, you can pick either point. It doesn't matter which one. It'll be the same line. It'll just look different. So the vector to this point, you just put angle brackets. Remember, the round brackets are the coordinates for the point. The angle brackets are the components of the vector. And if you put them at the origin, the components will be equal to the coordinates of the point. So R of t equals 2, 5, the vector to the point, plus t times the vector between the points, 6, 2. It's as easy as that. There's the vector parametric form for the line that goes through 2, 5, and 8, 7. You know, I called this 2. I guess it was 2B over here, wasn't it? It was the three-dimensional case. I call this 2B. I hope I gave it 2B, the three-dimensional. All right. So there's the vector parametric form. Looks like that. And then we can make an interesting note on this. Because we picked the vector B by subtracting these components, what's going to happen is this. If we take t equals 0, we're just going to get R0, the first point, 2, 5. Right, because we're taking R of t when you take t equals 0, you just get the point, right? So this will be R0 goes to that point. And if you take t equals 1, then you've got R0 plus the vector here, 6, 2, that goes between the 2 points. So if you're taking the vector, the first point plus the vector between the 2 points, you get to the second point with coordinates 8, 7. In other words, if you use t equals 1, you're just adding the 2 vectors there, and you get to the second point. So this would be R of 1 because you took R0 plus 1 times 6, 2 to get to it. Consequently, we know that R of 0 is 2, 5, the components of the first point. If we take R of 1, we get the vector the second point, 8, 7. And I forgot to put something in here. I said, let's get vector parametric form and parametric equations. So, what are the parametric equations? You can just say either by equations 2 or by looking at this. What you have is the x component, x equals 2 plus 6t. Equating x components. the second component y is equal to second component 5 plus 2 times t here. So this first one is the vector parametric form, and then if you just equate components, or if you write equations too, x0 plus at, y0 plus bt, you get the parametric equation. So there's the line, that's part one. And then we notice that r of 0 is the 0.25, and r of 1 is the second, goes to the second 0.27. Therefore, if we put in b here, find parametric equations of the line segment. What do we do? The segment between the 2 points. Tip. R0 gets the first point, R1 gets the second point. It moves continuously between the two, right? This is continuous functions here. And so it's just the same equations. X equals 2 plus 6t. Y equals 5 plus 2t. But restrict t between 0 and 1 instead of letting it go from 0 to minus infinity to infinity. So there's parametric equations for the line segment. But it's really easy working with these things. Lines are easy. R is R0 vector to one point of the line plus t times a vector parallel to the line. And you've got equate components, you've got parametric equations. You want the segment, you just take the parametric equations and let t run from 0 to 1. Nothing more. And it works in 2 dimensions, it works in 3 dimensions, it works in higher dimensions. It's just harder to draw, right? So you can do this in any. Okay. Here's an example. Let's do some lines in 3 space. Ask, do these lines intersect? I was interested when we like equations for lines intersect or not. Don't have to in 3-dimensional space, but in 2 dimensions, they're either parallel or they intersect. But in 3 dimensions, it's less obvious. You can have one line going up like this, another line coming down from the back, and they don't have to be in the same plane. They can be, one way up over above, and there's some distance between them. And they just skew lines, we call them, S-K-E-W, skew lines. Lines that don't intersect free space aren't parallel. So maybe these are parallel, don't intersect. Maybe they're skew lines. Maybe they do intersect. So that's pretty lucky. You have to put them in the right place. Well, let's try these lines. X equals minus 2 plus 2t. I'm sorry, 6 minus 4t. And z equals s1 plus t. That'll be an equation for one line. Parametric equation. Let's call it L1. Line L2 can have these parametric equations. X equals 2t y equals minus 2 minus 2t, and z equals 2. Do these lines intersect? So these are both lines, right? It's a plus bt, a plus bt. A and b can be 0, so some or both of them. It's still a line, as long as you don't have a, b, and c all 0. You have to have at least one of the components of the direction vector non-zero to generate the line. So it actually has a direction. So here's 2 lines. Do they intersect? How do we tell? They intersect if they have a common point. When you see this in the problem set, it's on your homework. The trick to doing this is just to say, wait a minute, t is just a parameter. These don't have to intersect at the same value of t, they just have to have the same coordinates where they intersect. So I'll just scratch this out and call this one s because it's not the same t as up here. And so you call the parameter in one equation s or u or whatever. What I need for them to intersect is to have x and y and z all be equal. And the easy way to do that is to take and say, well, where they intersect, these will be equal. So we can equate the x components and say, if they intersect, then we have the x components equal minus 2 plus 2t has to be equal to 2s, the parameter of the other equation. And 6 minus 4t has to be equal to minus 2 minus 2s. So you equate their x and y components. And now this is an easy game because I don't know if some of you have linear algebra before. Most people take it after this class, but linear algebra is the study of linear equations, primarily systems of linear equations. And you find out in there that every system of linear equations, you can always find a solution or so that it has no solution. So this system of two linear equations and two unknowns, we simply usually write it in this form. We'll write minus 2s by subtracting this over, plus 2t equals adding 2 to each side equals 2. So I'll write the first equation in that form by adding 2 to each side and subtracting 2s from each side. Then I'll do the same thing here. I'll add 2s to both sides. 2s minus 4t equals, let's see, I subtract 6 over minus 8. So I write the s's here and the t's here and the numbers on the right-hand side in convention. Then it's very easy to work with. If I call this equation 1 and this equation 2, you can either solve for one variable in one equation and substitute it into the other, the method of substitution, and that works. However, you find when you get to 3 equations, it's kind of complicated, and 4 equations, it's really long. But 2 equations, it works quite well. You can do that if you want. What I'm going to do instead, I'm going to show you how to do elimination. In elimination, there are 3 operations you can do. You can reorder the equation. Who cares? It's the same equation. You can multiply an equation through by a non-zero number, or you can add a multiple one equation to another, replacing that latter equation. And what you do is you try and eliminate variables doing that. And there's an orderly process called Gaussian elimination, named after the great Gauss, that always works, and you can prove that it always gets the solution and shows that no solution exists. So, but we don't have to use Gauss's method. We can pretty much figure it out without that. For instance, how could I eliminate either s or t by taking a multiple of one of these equations, add it to a multiple, add it to the other equation? Well, I can just take 1 times the first equation and add it to the second equation. Minus 2s plus 2s is 0. I get rid of the s's that way. That's why I picked this. If this was minus 4s, I'd add half times the first equation to the second equation. But you take a multiple of the first equation, add it to the second equation, or add a multiple of the second to the first to eliminate either s or t. I'll eliminate s here. Right, this plus this is 0. Then this plus this is 6t, and this plus this is minus 6. Oh, let's see, 6t equals, oh no, that's 6t. This plus this is minus 2t. Minus 2t equals minus 6. Now I've solved for t. I observe by dividing by minus 2 that t must be 3. Okay, so if t is 3, now I can plug that into either equation and find s. Let's put it into 1, it doesn't matter. Put into 1. to obtain, if t equals 3, I've got minus 2s plus 2 times 3 equals 2. So I subtract 2. Evidently, s equals 2. So that's the values of s and t that are required in order to make the first two equations match, or x and y equal. Now the trick is, does that make z coordinates equal? Right? If the z coordinates are now equal that same value of s and t, then they intersect, and if the z coordinates aren't equal, then they're skewed, they're running over each other. Where the x and y coordinates are equal, z is the different numbers, right? That makes the x and y coordinates equal, only those values of s and t. The lines intersect if and only if, all right, IFF is mathematics short for if and only if, z coordinates are equal for these values. So the big trick here is to change one of the parameters to a different letter, since the parameters don't have to be equal where they intersect. So we just plug it in. Z equals minus 1 plus t is 2 in the first equation, L1. And then L2, z equals 2. S isn't even in there. Sure enough, they're equal. These lines are. But you can put t equals 3 in the first equation or t equals 2 in the second one. It doesn't matter. S equals 2 in the second, let's say. It's a little easier, right? X equals 2 times S is 2, is 4. Y is minus 2 times S is 2, is 6. And Z equals 2. I'll put a stroke through the Z here to show it's a letter when my 2 won't have a stroke. So it intersects at the point 4, minus 6, 2. We're lucky these do intersect, right? You pick arbitrary lines, they probably won't intersect. That's what you do for those. So pretty easy working with these in general. Let's try this one. One of the fun things is in calculus 1, you can do tangent lines to a curve, right? It's real easy. You just find the derivative and right, and that gives you the slope, and then you plug it in. You have the points. You plug it in the point slope form. You get a tangent equation to a curve, right? What about a tangent? As I said, find parametric equations. Now, since we're in 3 space, we'd rather use parametric equations. Otherwise, we'll wind up writing 2 equations for a plane or something silly like that. Find parametric equations for the line, a tangent line, to the curve, given parametrically by x equals t, y equals t squared, z equals t cubed, at the point where t equals 2, which is the point 2, 4, 8. I just plug that in. Plug in t equals 3, get 2, 4, 8. So there's the point. Well, boy, that's pretty easy. The tangent line goes through this point, so I can just let that be x0, y0, z0. And I'm thinking, all I need is a direction vector, right? I have the point, I have the all I need is the direction vector. So what you do is, this is leaning ahead a little bit, but the direction of the tangent, we'll say shortly, is dx dt, y dt, is the tangent direction. And so at t equals 2. You get this tangent vector at that point. Well, the x dt is 1, the y dt is 2t, and the z dt is 3t squared. We're going to plug in t equals 2. Now we get the vector is 1, 4, 12. So this is your A, B, and C. Now I can construct a tangent line with this curve. I just write down equations 2b. By 2b, which said x equals x0 plus at must be 2 plus 1t. Y equals y0 plus bt. All I need is the point in the direction vector, which is then 4 plus 4t. And z is equal to c0 plus ct. That's 8 plus 12t. And then you can leave out the stuff in the middle. X equals this, y equals this, c equals this. Our parametric equations to the line. So very nice result. That's it for lines. All right, so next topic then is planes, and we're going to get even more exotic next time we get to do quadratic surfaces, which are real beautiful. I think you'll enjoy those a lot. Maybe we'll get a little bit of them at the end here. I'll look down it. Now we're talking three space because in x, y space, there's only one plane, right? So in three space, how can we describe planes? And you can actually do higher dimensions too, right? If you take a flat subspace of three-dimensional space, we call it a plane. If you take a flat subspace of four-dimensional space, it's a three-dimensional subspace of four-dimensional space. We call it a hyperplane. You get these shades of Star Wars coming in hyperspace and so forth. There's n-1 dimensional surfaces in n-dimensional space, but hyperplanes are flat surfaces. And so this extends to higher dimensions, but it's harder to draw. Let's just, the main purpose is planes of three space here. Now, how can we describe a plane? We construct a plane somewhat analogous fashion. We consider any point on the plane in three space. X0, Y0, Z0. And we'll draw it like this. We make sort of a parallelogram, and it looks like a tilted rectangle. And it actually extends out to infinity, right? It's a plane. Close enough. All right, and then if you have that point, and suppose you have a vector b as before, let's give it three components since it's in three space, A, B, C, that's perpendicular to the plane. We can construct the plane as follows. We'll define actually a plane to be the set of all points in three space, x, y, z, such that, suppose we construct this vector R0 out to x0, y0, z0 from the origin, then it's the vector with those components, x0, y0, z. A point that then R0 defined to be the vector to that point. is given on the plane. And if we define R be the vector to x, y, z, the arbitrary point in the plane, R minus R0. What vector is that? That's the vector from the end of R0 to R, remember, right? It's the vector that goes between the endpoints. And I should have called this R0 over here. This one's R0. R minus R0 is this vector from end of R0 to R. Right, so that when you add it to R0, you get R. This one, oh, you know what, instead of V, let me call this N. The book called this N, I just remember. N for the normal vector. With R minus R0 perpendicular to a given N with some components A, B, C, not all 0. Otherwise, it's just a 0 vector. It doesn't have a direction. Called the normal vector. So you're given a point and a normal vector determines a plane. And what this is saying is that it's the set of all x, y, z. But since this given vector n is perpendicular to the vector from the point that you know is on the plane to the point you are checking. If those are perpendicular, then this is a point on the plane. So the idea is perpendicular to the normal, but this is not a point in the plane because these are not perpendicular. So that'll define a plane. You need a point and a normal vector. Well, what is that? Equivalently, this is R minus R0 dot n equals 0. That's what orthogonal means. Perpendicular means is that the two vectors dot product is 0. So we can call this the vector form for the plane. I don't use this one much. Instead, if you write out the components, this is, well, this vector here subtracts the components of R that goes to an arbitrary point in the plane x, y, z, minus the vector to x0, y0, z0, the given point of the plane. So it has components x minus x0, y minus y0, z minus z0. That's the components of R minus R0. And then dot n, n is the normal vector whose components we called A, B, C. And then it has to be equal to 0. Well, this is zero. This is by definition of the dot product. A times x minus x0 plus b times y minus y0 plus c times c minus z0 equals 0. That one we will call point normal form for the equation of the plane. In other words, given a normal vector ABC and a point on the plane x0, y0, 0, 0, take all points perpendicular to this vector is equivalent to saying this equation holds. So that's what you want to do. To find a line, you find a point on the line and a vector parallel to the line, you immediately write down equations 1 or 2. Find a plane, you find a point on the plane and a perpendicular vector to the plane, and immediately write down this equation. We can call this 3. Now, if you multiply this out, this is the most important equation, though. Multiply out, you get ax plus by plus cz well, let's say minus, no, it's what, plus, minus ax0 minus byz0, 0, minus cz0, all equals 0. This is multiplying out, grouping. And now if you say, this is just some number, let's call it d. We observe that we have ax plus by plus cz plus d equals 0 is the general form of the equation for a plane, where again, a, b, and c can't all be 0, or, right? So every plane, just like we said, here's the general form for an equation for a line in the plane, x plus by plus c equals 0. That's the general form of equation for a line. When a, b are both 0, this is a line. Every line can be put in this form with a, b not both 0. Similarly, every plane in 3 space just has one more component, x plus by plus cz plus d equals 0. Every plane has this form with a, b, c not all 0, and every equation this form with a, b, c not all 0 is a plane. So maybe I should be clear on that. A, b, c not all 0. That was our starting point. We had to have a non-zero vector for the normal vector. At least one of them has to be non-zero. So we call this equation 4. I don't think the book gives it a name. But see, this is how you know an equation. If it's a linear equation and a and x, or 2 variables x and y, then it's a line, right? And this is a linear equation. A linear equation of 3 variables is a plane. Has a flat subspace of 3-dimensional space. Now we've got nice equations. And it's a lot like doing algebra before. If somebody gave you a y-intercept and a slope of a line, what did you do to write the equation of the line? You wrote y equals mx plus b, of course, right? You have the slope of the y-intercept, you had m and you have b, so you just wrote that down. If somebody gave you a slope of the point, you wrote y minus y0 equals m times x minus x0. That's the point slope form. You've given a point and a slope. And so you just plug in what you had. What we observe here is these are the only way we're going to do this. Somebody gives me a point and a normal vector of a plane, I immediately write this equation down, the point normal form, just like slope intercept form of the line there, point normal form of the plane here. And then if by chance, once in a while I can use this equation instead. If I know, for instance, it's a parallel plane, you notice that in this thing, what are A, B, and C? You know immediately what the normal vector is just by looking at the equation of plane as ABC. If you know a normal vector, sometimes you just use this equation of plane and find D right away. And so this equation sometimes works just as well, but this one is real nice, and we'll take that as our first choice. Those 2 equations will serve for finding our plane. So here's an example. Find plane that goes through, I'll write an abbreviated through, point -1, 2, 7, and it's parallel to the plane x minus 2z, x minus 2y, excuse me, plus 4z equals 0. How about that? here's an interesting note. What is one point on this plane immediately? Obviosity, I guess you call it. If you plug in 0, 0, 0, you get 0, right? Any plane x plus by plus cz plus d equals 0 with d equals 0, I can put d on the other side, is a plane through the origin. So d is a big hint there. If d is 0, then it's plane through the origin. If d is not 0, then it does not go through the origin. Here's a plane through the origin. We want a plane that goes through this point. Maybe this contains that point anyway, but likely, right? Right. Well, we know that it's a parallel plane, right? That's given. Since it is parallel, it has the same normal vector. Also has, well, you just read it off here. A is 1, B is -2, C is 4, right? In the standard equation, 4. It also has the form by 4, x minus 2y plus 4z plus d equals 0. Right? Every plane has this form, and we know it has the same ABC, same normal vector, since it's parallel. So this is the plane. All we have to do is plug in this point now and find out what d is. Plug in -1, 2, 7 for x, y, z. Find out what d is. So we got -1 minus 2 times 2 plus 4 times 7 plus d equals 0. And let's see, -1 minus 4 is -5 plus 28, 23. Evidently d equals -23. And the equation of the plane, 3s means therefore in mathematics. Therefore, x minus 2y plus 4z minus 23 equals parallel to this plane because it has the same ABC normal vector. 1 minus 2, oops, 4 times z. 1 minus 2, 4. And if you plug in -1, 2, 7, you find you get 0. So there's an easy one. Here we can use the form 4, the standard form. Sometimes that's not the case. By the way, the point normal form is especially nice for finding tangent planes to surfaces. We're going to, like, well, next semester. But just like in calculus 1, if you do a point and a slope of the tangent, you can immediately find the tangent line using the point slope form of the line. Similarly, now in calculus 4, you consider surfaces. D is a function of x and y. And if you know one point, and you take the one point of tangency on the surface, x0, y0, z0, and you can construct a tangent plane by simply finding a normal vector of the surface. And so this point normal form is what gives you the tangent plane, just like the point slope gave you the tangent line. It's generalizing to more dimensions what we've done in calculus 1 here. All right. Example, find the plane, it's a tricky one, containing the 3 points, 1, -2, 0, 0, 1, 4, and 2, -3, 5. Just like 2 distinct points determine a unique line of the plane, 3 points not all on a line determine a unique plane in 3 space. You kind of visualize that, but it's true. Here's how you can prove it, actually. If you took these 3 points arbitrary, not on a line, you could do a similar construction to this that we do to construct the actual plane going through these points. How can we do this? Well, let's call this point P, call this point Q, and call this point R. With these, and we'll say the vector from P to Q is gotten by subtracting the coordinates, right? You just take 1 minus 0. P to Q, I take 0 minus 1. You can do the other one, it doesn't matter. But 0 minus 1, 1 minus negative 2, and 4 minus 0. There's the vector from P to Q. It's negative 1, 3, 4. To R, say, right? By subtracting this, the R coordinates minus P coordinates. 2 minus 1, minus 3 minus negative 2, and 5 minus 0. So the vector from P to R is 1, minus 1. These are two vectors in the plane, right? Because they go between two, each one of them goes between 2 points in the plane. Now you ask yourself, how can I find a vector perpendicular to the plane given 2 points in the plane? Go back to last lecture. I find a vector perpendicular to two given vectors. Here's two vectors, maybe PQ, PR within the plane. Find a normal vector. What if I took PQ cross PR? Remember, the cross product is perpendicular to both vectors by the right-hand rule, so it'll be this way. Here's PQ cross PR, and we could take that or any other vector that's perpendicular to be the normal vector. Doesn't matter if it's by the left-hand rule, just so it's perpendicular to the plane. So we choose equals PQ cross PR is, well, we can use the determinant. Okay. By the way, I should mention somewhere along here, there was one of those famous physicists, I've forgotten which one, who developed a nice rule for doing this. Here's P, and here's PQ, and here's PR, 1 minus 1, 5. So we need this determinant, right, to get the cross product. One of the physicists did this, he just repeated the I and J columns. He liked to do this, minus 1, 3, 1, minus 1. And he would take this diagonal, I think, minus these, or probably what he did, this one minus these, or can't remember quite how he did this, but he would write out 2 extra columns, and then he wouldn't have to go back and forth so much somehow. You'll see people do that sometimes. I see students do that. But here's how we did it, and how most textbooks do it. We say, oh, this was I times the subdeterminant got by wiping out its row and column. 3, 4, 1 minus 5. Minus 1, 5. And then minus J is plus minus plus. Times the determinant got by wiping out its row and column. It's minus 1, 4, 1, 5. And then plus K times we wipe out its row and column and get this matrix left, minus 1, 3, 1 minus 1. By the determinant formula. So it's I times 15, this diagonal minus this diagonal. 3 times 5 minus 1 times 4, right? And this one is minus J times minus 1 times 5 minus 1 times 4 plus K times minus 1 times minus 1 minus 1 times 3. There it is. And so I get, say, 15 plus 4 is 19I. And then minus 5 minus 4 is minus 9J. And then 1 minus 3 is minus 2K. Well, those are big numbers. Maybe I made a mistake. We didn't talk about this last time, but I've been wanting to do this. This is a good opportunity. What if I'm worried I made a mistake? What's a quick and easy way to check this? We said that the cross product is always perpendicular by the right-hand rule to the two vectors that went in. So we can check it and see if it's perpendicular to this row and this row, the two vectors that went in. I should be able to take the dot product, right? This times this plus this times this plus this times this should be 0 if they're really perpendicular. Same here. This times this plus this times this plus this times this should be 0. So let's try it out since I'm worried about these numbers. Minus 1 times 19 is minus 19. There's another minus 27. And then minus 8, that can't be right. That's negative. That's not 0. So I got a mistake somewhere. What did I do? Well, let's see. Here's a mistake. I've got minus 9 in here and minus. It's plus 9. Here we go. Now let's try it. This times this is minus 19. Plus this times this is plus 27 makes 8. And this plus this times this is minus 8 is 0. Now I can see the orthogonal. And then we check the last row. This times this is 19. Plus this times this subtracts 9 is 10. Plus this times this makes 0. So sure enough, it's perpendicular to both these rows. It's probably right. The dot product is with the two original vectors, see if it's 0. Well, now this is A, B, and C for the plane, since it's perpendicular to both of the vectors in the plane. We can take any one of these 3 points as the point in the plane. Let's just choose the first one to be easy. And so now we immediately write the point normal form 3. I should just copy it again since I had to erase it. By equation 3, which was A x0 plus A times x minus x0 plus B plus y minus y0 plus C times C minus Z0 equals 0, the point normal form. We have A is 19 times x minus x0 was 1 plus B was 9 multiplies y minus y0 was -2 plus C -2 multiplies Z minus Z0 was 0. All has to be equal to 0. Well, you don't like to leave it in this form because it's messy. Leaving it that way, there's too many numbers, right? So you multiply it out in group-like terms. You have 19x, 9y, minus 2z, then minus 19 from here, plus 2 times 9 is plus 18, and plus 0 here. Evidently, we can simplify this and write it as 19x plus 9y minus 2z minus 1 equals 0. There is the standard form. Just like you like to write equations for lines either in slope-intercept form, y equals mx plus b, or sometimes in general form, x plus dy plus c equals 0. To make them easy to read, just so we like to put these into the form for simplicity rather than leaving it in point normal form. Okay, x plus by plus cz plus d equals 0. A linear equation, 3 variables in the plane. How about this one? X minus 2y plus z equals 0. 3x minus 3z plus 5 equals 0. Are those planes perpendicular? They're both planes, right? X plus by plus cz equals d. X plus by plus cz plus d equals 0. We know they're planes. Are these perpendicular planes? How do we know? Really easy. And 1, the first one, you just read the coefficients. 1 minus 2, 1. The coefficients of the variables are a normal vector of the plane. So this one has normal is a normal vector of the first plane. We read this one off. 3, 0 minus 3 is a normal vector of the second plane. Are the planes perpendicular? They're perpendicular if and only if their normal vectors are perpendicular. Since n1, to put vectors on them, they're vectors, dot n2 is equal to, well, let's see, 1 times 3 plus minus 2 times 0 plus 1 times negative 3, in fact, is 0. Since the normals are perpendicular, yes, the planes are also perpendicular. Above that. That shows that it's easy to find a normal vector of the plane. You just read 1, 2, 1. Furthermore, you can actually find the angle between two planes. Usually by the angle between two planes, we mean the smaller of the two angles, because if you take two planes, right, here's one plane and here's an intersecting plane. They intersect in a line. If they're not parallel or coincident, then they'll intersect in a line like that. When I say the angle between the planes, I mean the smaller angle, the acute angle, theta. I didn't draw that very well. This plane is supposed to look like this. There we go. So here's the line of intersection. And there's the angle theta between the planes. Find the angle between planes. X minus y plus c equals 4. I like to write these equations x plus by plus cz equals d with d on the right instead of on the left. Other books do it that way. You can do it either way. The reason being that this is the way you like to write equations in linear algebra. And the plane 2x minus y plus 3z equals 4. I suppose we have those two equations. What is the angle between them? How do we know there's an angle between them? Maybe they're parallel. A normal vector, right? But ABC here would be a multiple of the ABC here. They'd be parallel vectors. Since they're not parallel vectors, these planes do intersect. But the way we can find the angle between them, and we're interested in the acute angle, smaller of the two angles here, not this one. It's also the angle between the normals, right? Take this normal N1 and this normal N2. And this is also theta. So the angle between the planes will be the angle between the normals, although you got to be a little careful, because if you chose this for the normal N2, now you're going to get an obtuse angle between the vectors. You have to subtract it from 180 to get the acute angle. So it's the acute angle. It's either the angle between the normal vectors or 180 minus that, depending on whether the angle you get between the vectors is acute or obtuse. So here's what we do. We say the normal to the first vector plane, you just read the coefficients. 1 minus 1, 1. 1 minus 1, 1. The normal to the second plane, 2 minus 1, 3. How do I find the angle between two vectors? The dot product. Remember this formula? Theta is always the arc cosine, as long as you don't have a zero vector here, of n1 dot n2 over length. It's because n1 dot n2 is length of n1, length of n2, cosine of the angle between them. You solve that for theta, the angle, and you get this. This is the formula we wrote for angle between two vectors. So let's see. N1 dot N2 is 1 times 2 plus minus 1 times minus 1 plus 1 times 3. And then the length of N1 is the root sum square of its components. Oh, that's evidently square root 3. And the length of N2 is the root sum square of these. 2 squared plus minus 1 squared plus 3 squared square root, right? Which is square root of 14. So it's actually the arc cosine of 2 plus 1 is 3 plus 3 is 6 over square root 3 square root 14, which is the arc cosine. So 6 over square root 42. And you can run that on a calculator. How do I know I don't need to subtract 180? I subtract it from 180. Sine of an angle is positive, it's an acute angle. So had this been a negative number here, I'd take 180 minus or pi minus this. But since it's a positive number, I just take the arc cosine. There it is, that's how you get the angle between two. There's a problem like that on the home. But it's fine. One last formula we can do. This is where it would be nice to have the book. The book has a nice picture. You can take a look at it. I'll roughly replicate it here. Suppose we want a distance from a point, x0, y0, z0, to a plane. What the distance is? Well, it means you drop a perpendicular. It's the shortest distance between all points in the plane. So you want to drop a perpendicular. How can I find that? The answer is this. You just take any other point on the plane, x1, y1, z1, any point in the plane whatsoever. Actually, yeah. Yeah. I can take this vector and call this point P and this point Q. I should call it the other way. Let's call this one P. P and Q. If we take the vector and this normal vector n, it's the length of the projection. So distance equals the length of the projection of PQ onto n, which is just the vector ABC, right? So n is ABC, maybe I should write it from the plane equation. And if you work that out, you get this nice formula that the distance is actually equal to absolute value of AX0 plus BY0 plus CZ0 plus D over square root A squared plus B squared plus C squared. Well, I'll say on the test, actually, you can figure it just by doing this. It's not very hard. I'm out of time here. But if you shoot what this formula does for general A, B, C, and X or Y0, 0, 0, by algebra reduces to this formula, which we can call phi. It gives a nice formula by this planes we've been doing for the distance from a point to a plane, famous kind of problem you need to do. So if I say example, how far from the point 1, 1, 1 to the plane x minus 2y plus z equals 0 that goes to the origin. How far is it? 1 minus 2, 1, a, b, and c. We call this x0, y, z, 0, and all you have to do is plug in. So you say the distance, this is, maybe I should call this dist instead of d from the plane, dist. Dist is then this times this, 1 times 1, plus this times this, minus 2 times 1, plus this times this, 1 times 1, all both in absolute value. All divided by root sum square of a, b, and c. Square root of 1 squared plus 2 minus 2 squared plus 1 squared is square root of 6. So it's evidently 1 minus 2 plus 1, 0 over square root of 6. That's because this plane contains the point. So the point is on the plane in this case, but it works in general. All right, here's put the homework up for this time. Here. So fun with points and planes. This actually covered 2 sections tonight. How about that? Just because the section on lines is really easy. Remember the section numbers, it's 11.5 and 11.6. So on 11.5 on lines, there are easy problems. Look at 3 to 17 odd. You might just look at a lot of these and say, oh, yeah, I can do it. Yeah, I can do it. 29 and 33. And then 11.6 on planes. These are a little hard. You should do them all. They're not hard. Just do 3, 9, 11, 15. But there'll be problems like this, 3 points, find the plane, find the angle between the planes.
We're gonna make all those in chapter 12 this semester?
I never do the last section in chapter 12 because it's Kepler's laws and it's not very useful. We're so short on time anyway, so we're going to skip that. I intend to skip some of the material just before that. So we're going to do most of chapter 12, but not all.
When is school out?
We have 2 more weeks after this and then finals. Everybody for coming in.